Good morning, everyone. Hopefully, everyone had a great weekend. We are going to get started today with the discussion of volcanoes. We'll mainly discuss their role as, uh, geological hazards, a little bit about their implications for climate, and then also conclude with some important aspects about how they're sort of very relevant to society in terms of beneficial aspects as well. So if you I got some questions with this. Again, I talked about this during the lecture that there was no worksheet last week, but there is one posted for this week. It should already be online, and it goes till Friday, where it's due by 11:59 on Friday, which will mainly cover some of the questions about volcanoes and tsunamis that we didn't get into during the last week. So without any further ado, here's an example of one of the volcanoes. This is actually an image of Mount St. Helens from an aerial photography, looking at the plume of explosive dust that's basically being released from Mount St. Helens back in 1980. We'll come back to Mount St. Helens plenty of times throughout today's lecture. It will be an example of a lot of the geological hazards tied to volcanoes that we'll discuss. So just to give you a sense of where there are actually volcanoes in the U.S., most of the active volcanoes in the United States are in the Aleutian Islands. So this is in Alaska, this archipelago from Alaska that extends out to the west of Alaska. Of course, Hawaii over here is a major Hawaiian area. But what many of you may know less about is actually the series of volcanoes in the Cascadia and along the western margin of California. So there actually are several active volcanoes in the western margin of the United States along that plate boundary as well. Specifically, Mount St. Helens is up here in southern Washington, but there are several others. The Three Sisters, Glacier, Mount Rainier, that are in this area that are actually still active, although the ruptures haven't been nearly as recent. There are some other areas here near Mount Shasta and Lassen where there's very active magma bodies in the area that actually experience activity and are still very clearly active. And then, of course, last but certainly not least is the Yellowstone volcanic field, which is a major mantle plume we talked about earlier in the semester. What probably, those are the main volcanic areas. They certainly tied to the concept of the active plate boundaries. But where many of you may not realize that there's also recent volcanism. Some cases recently as the last 600 years in central Utah and around basically around the Colorado Plateau. So over here in Colorado, southwestern Colorado, central Utah, and what's called the Basin Range province, there is some evidence of active volcanism in those areas, and that's related to the subduction of the Pacific plate, or the Farallon plate, as we call it, below North America, which is causing that area to sort of start rifting and volcanism in that area. So all these areas are active relatively recently. The Bandera Field in New Mexico, San Francisco Field, if anyone's been in Flagstaff, all those areas surrounding the Colorado Plateau have experienced, which is an old cratonic component of old geological rocks. There are some very active areas in this area. Some of these in Colorado actually historically documented in the area. But nonetheless, most of the volcanism you actually see is in the Aleutians, of course, in Hawaii, which are active on Hawaii is active on a day-to-day basis, and along the western margin of the United States. So, for perspective, worldwide, there's about 50 to 60 volcanic eruptions a year. Some of those are things you hear about in the news, causing flight disruptions or causing major tsunamis or hazards. Others, which we'll talk about throughout the lecture, are areas that are continuously active and erupting lava almost on a continuous basis and are sort of always in that class. Certainly the Mauna Loa or the Loihi and some of the volcanoes in Hawaii are active on a daily basis. There's some other examples that I've worked on through my own research in East Africa, particularly in Ethiopia and in the Democratic Republic of Congo, that are active so frequently that there's actually something called a lava lake where it's continuously bubbling over. And I'll show you some pictures of that a little bit later on in the lecture today. So give you a perspective on the amount of actual direct deaths in terms of geological hazards. In the last century, this is 1900 to 2000, about 100,000 people were killed by volcanic eruptions. In the last, since the turn of the 20th century, 2000 to 2020, about 23,000 people are killed. So We're getting close to a quarter of the way through the century and have killed about 100, about 100, about a quarter of that 100,000 have been killed, this century as well. Obviously, as we go on through the lecture today, we'll talk about this, but there's other implications for humanity besides death here in terms of sudden climate changes, and hopefully by the end of the lecture today or later this week, you'll come to the conclusion that there can be major societal influences from volcanoes that we'll talk about as we go on. So, in addition to areas like Seattle, Seattle is one of the areas that's considered to have a very high geological hazard risks, actually probably much more than either Los Angeles or San Francisco, even though we tend to talk about, those areas because of earthquake hazards. Seattle has sort of a triple threat in the sense that there's always potential for major earthquakes in the Juan de Fuca plate just off the margin of Seattle. There's some potential for tsunamis, though it's relatively protected by the fact that it's wrapped around in the sound. But more to the point is that there are a series of volcanoes that are active and nearby that can cause localized problems. So there are some volcanic ash and pyroclastic flows in the area just southeast of Seattle, quite close to the town, indicating that on a geological time frames, the area can be influenced by sort of volcanic hazards as well as some of the other tsunami and earthquake hazards I just mentioned. Some other examples of cities that are, particularly prone to a variety of geological hazards. We've used Mexico City as an example of an area that's experienced really profound earthquake in the last, within the last century. And we showed you all the pictures of the damage in the 1980s in Mexico City. But this is another example of an area that's very prone to active volcanism as well. So you're going to notice a trend here, right? Areas near plate boundaries tend to have a lot of earthquake activity, a lot of volcanic activity, relatively speaking. Certainly that means they have opportunities for tsunamis and other geological hazards. But as a result, where geology happens, geology happens. That sounds like a really dumb statement, and to a certain level it is. But most of the activity is in the areas where there's active plate boundaries interacting with each other, particularly along the Pacific Ring of Fire or Pacific Ring of volcanoes and whatnot, that we use those words interchangeably. So, without any further ado, this is the general idea of the Ring of Fire that surrounds Pacific plates. It surrounds the Pacific plate and contains 2/3 of the active volcanoes. If you were to look at this area, this 2/3 of the active volcanoes, and almost all the rest of the volcanisms along the Mid-Atlantic Ridge and along the East African plate, with some other volcanoes in the Indian Ocean around Indonesia. So the Pacific Ring of Fire is the area of most active activity. And the key thing I want to point out to you here is that in all aspects, you have the Pacific plate that progressively older towards the margins or outward from Hawaii, oceanic plate that's dense and subducting beneath the continental plates around it. So it's almost all driven by subduction of the Pacific plate in those areas along the Ring of Fire. Of course, these examples I gave you in the Mid-Atlantic Ridge and in East Africa are examples of divergent plate boundaries where this is sort of spreading out, and there is plenty of volcanism in those areas as well. So, let's start with some of the basics. A lot of these are words you've certainly heard and possibly, likely even know the definitions of. The one I'll bring up first is the definition of magma. Hopefully everybody knows what this is, but it's molten rock, often mixed with small components of dissolved gases, or in fact, relatively large components of dissolved gases that are basically generated in the subsurface. So by definition, magma cannot be above land surface. At that point, it becomes lava. But again, these can often have different compositions that can influence their behavior, their eruptive style. But it's basically a mixture of gas that can be water, CO2, sulfuric oxide, mixed with molten rock or melted rock, which encompasses all the minerals that are around those areas. Again, just like we talked about in terms of where volcanoes occur, the material that, the magmatic material is basically generated near the plate boundaries, near divergent, convergent plate boundaries, although there is some volcanism near transform boundaries as well. And then again, once that magma reaches the surface, whether that is the surface of the atmosphere, if it's on land, or the surface of the ocean, If it's on, if it's underwater, it is called lava. So you can have what's called subaerial volcanism, meaning that it's erupted onto the surface, or you can have subaqueous uh, volcanism, which means it's erupted into water. So there's plenty of examples of that within things like volcanic eruptions in Hawaii, where there's aqueous or submarine, some people call it, volcanism, where it discharges magma, which becomes lava at the surface of the base of the ocean. Key thing here is that most of the behavior, particularly with regards to hazards for magma, is going to be determined by the viscosity. And you can think of viscosity as the pourability. I think we all recognize that, if you take water, ketchup and peanut butter, they all don't pour at exactly the same rate. And as a result, how the viscosity of various magmas vary, which by the way, they vary according to the mineral composition, largely the amount of quartz or silica, Si from the periodic table in them, will dictate the likelihood that there will be flow. And in general, the more silica content, the more peanut butter-like it is, and the less silica content, the more fluid it is. So if you see, and we'll talk about this as we go on, but if you see the examples in Hawaii of the fast-flowing pohoihoi lava that just rolls right down the hill, that's relatively low silica. The big blocky, slow-moving things just kind of plop out. That's what's called lava, which has a higher silica content. But the key thing here is that in terms of understanding hazards, and in terms of understanding the chemistry of the magma, basically the amount of silica, will determine the composition and the hazards, as we'll discuss as we go along. So when I ask that question to you on an exam, what determines magma's viscosity? I want everyone to remember the answer is silica content, right? Silica content is what's going to determine how viscous it is, or how, and with increasing silica content, that becomes more viscous, slower moving. And the general trend in here is that the slower moving, more viscous, the more likely it is for pressure to build up and explode, as opposed to something as low silica content just flows out. Basically, that's where you see those images on the news of lava flows in Hawaii, or people just walking right up to it because it flows so predictably. It's like a creek. There's not really much concern it's going to spill out and sort of burn you. The second factor, of course, is temperature. Obviously, with enough heat, with a high enough temperature, everything becomes molten and can flow relatively rapidly. So even high silica rocks, if they're heated high enough, to high enough temperatures, I should say, they can actually flow as well. But in general, the key thing I want you to consider here is that magma's viscosity is controlled by the silica content. So let's talk about the specifics of magma generation. There's sort of, I suppose, three main sources or three main mechanisms of magma generation. The first one is actually the most volumetrically important on planet Earth, and that's what's called decompression melting or decompressive melting. This is the type of magma generation you see at the divergent plate boundaries. And basically the concept here is you have the Earth's mantle, okay, which is accumulating heat by the reactive decay of uranium, thorium, potassium we talked about earlier. And that heat creates basically, you can think of it as a critically stressed body of material. But because there's rocks that overlie those areas and it's under a lot of pressure, it actually keeps the magma sort of in a semi-solid, semi-ductile, ductile state. What happens is that when you actually see a divergent plate boundary spreading the plates apart and you remove that overlying weight, it's sort of like taking the lid off of a Coke can. It's not nearly as dramatic, for the record, but when you remove that pressure, it actually allows the material to basically go through what's called adiabatic melting or decompressive melting, and that allows this sort of semi-solid, semi-ductile magma to actually melt and form a liquid magma that can basically migrate upward and get to the surface. So the key aspects of this decompression melting is that the asthenosphere, the area below the lithosphere. Okay, so the lithosphere again is the Earth's crust and the uppermost solidified mantle. And in the cases near mid-ocean ridges or major divergent plate boundaries, that can be pretty thin. In areas like the Himalayas, major mountain belts, or under, for example, Ohio, the lithosphere probably is on the order of 80 to 150 kilometers thick, so pretty thick. It can be as narrow as less than 10 kilometers near the mid-ocean ridge spreading centers. But when the weight of that overlying lithosphere, again, crust and hard solidified mantle, moves away, reduces the pressure, and you can use the analogy to keep it organized in your head of taking the lid off the Coke bottle, allowing it to sort of not effervesce like a Coke bottle, but undergo decompression, melting, and cause magma to rise in the surface. So as a result, each sort of progressive plate movement away actually sort of remelts an underlying component of the mantle. The mantle will upwell beneath that area to sort of fill that hole, and will remain in a sort of ductile state until the point at which the pressure is released again and more material is melted by decompression melting and placed in that area. So key aspects of the asthenosphere is weak under the lithosphere plate. Temperatures, when you remove this pressure, you can get actually pretty low degree temperature of melting, as low as 1200 degrees is probably a little bit on the high end. But the key thing here is that the high pressures within the Earth's asthenosphere actually keep it in a solidified state until that pressure is released. Okay, so basically any scenario, just like where you have divergent plate boundaries in the mid-ocean ridges, you can see the material melting, and also you can think about it as a crustal thinning. So in areas like the East African Rift I mentioned, and we'll show you some examples of later, similar to what's going on in the Basin and Range province of the Western United States, in Arizona to Utah now, is as the crust is actually thinning, when it's getting pulled apart and it starts to thin, it allows some smaller degrees of magma to make its way up. And that volcanism I talked about within the last, 600 to 1,000 years in the Western United States, and even back as the last 10,000 years in Arizona, New Mexico, Colorado, Utah, are all related to that same process, just at a much smaller scale, because the plate section still remains quite thick in those areas. So the key idea here is that the mantle upwells in those regions. That means it literally convex and advex up into the space that's created when the lava, or when the magma is discharged to lava at the base of the ocean. And those decreases in pressure allow melting to occur and the magma to be released up to be in place as lava at their spreading centers. Okay, so again, decompressive melting is the way that drives the most of the volumetric amount of lava formation or magma formation on Earth. The second key aspect here is that, and which is mostly relevant at subduction boundaries, actually relates to the addition of volatiles. So the easiest way to sort of prepare yourself for the discussion of the addition of volatiles is to think about ice in the winter. We're unfortunately, hopefully, a few months away from seeing that and having to deal with that. But we all know if there's ice on the sidewalk, you can sprinkle some salt, and that sort of changes the melting and freezing temperatures of the ice, and actually causes the ice to melt at a much lower temperature than otherwise would. And in some certain sense, volatiles play the same role in the formation of magma. If you take a given rock, you bring it into the laboratory, fixed pressure, and you heat it up higher and higher temperatures, you can get a melting temperature. Okay. Well, just like adding salt to the ice, if you actually add volatiles such as water, carbon dioxide, hydrogen, or SO2 to the rock, but particularly, I'm going to focus on water here, it has the same effect. It actually causes the melting temperature to go lower and lower and lower, which means that a given body of rock or given body of the mantle, with the addition of more and more volatiles, you can actually make a magma form at lower temperatures and create magma that you otherwise couldn't generate. So the perfect example of this is looking at basically subduction zone related volcanoes in that Pacific ring of fire. And basically in that scenario, what happens is you have the oceanic plate. You can think of it being the Pacific plate, which is migrating, being subducted down below into the mantle. And for some terminology here, this is often called a mantle wedge, this little triangle here, where the plate drives its way down at some angle. And what happens is that as that occurs, you actually see things like water, calcium carbonate cement, or just calcium carbonate minerals. So basically, these can be little fossils or limestone deposits that form in the crust. When they get pushed down into the Earth's mantle, they basically break down at relatively low temperatures. Water in those that's accumulated in the pore spaces starts to become steam and be released into the mantle wedge. Calcium carbonate rocks can break down and form, what's called thermal catalysis. You don't need to know that fancy word, but basically it gets too hot and they break down and make carbon dioxide. The same is true for other volatiles such as sulfur oxide or SO2. And each of these components during the subduction process basically devolatilizes, or you can just think of it as vaporizes, and gets into the mantle wedge material. And that addition of volatiles, again, has the same effect as adding salt and reduces the temperature at which you can make it melt and creates magma bodies that can ascend slowly through the Earth's mantle and through the lithosphere and actually form volcanoes in subduction zones. So again, key ones I want you to remember here: water and carbon dioxide. These again are common in the oceanic crust, particularly in sediments in the oceanic crust, accumulated as that plate slowly moved over. For the Pacific, an example, the Pacific Ring of Fire. And water in the pore spaces, water in mineral phases, and carbon dioxide and carbonate in mineral phases all become volatilized at certain depths. So if it's not necessarily relevant to the hazard component of this, but if you actually think about a plate subducting down, the angle at which that plate subducts actually determines the temperature, the depths at which that body of rock will reach a temperature where devolatilization will occur. So if something's a relatively flat slab, you can imagine if it has to get down to 20 kilometers to start melting, that's going to be pretty far. If it's a steep slab, that can occur really close. And as a result, the distance that volcano is going to be located from the subduction zone is largely a function of the angle of the subducting plate and how far that, and basically dictates how far that is from the subduction zone. And that's tied to how deep you're going to get to where these different mineral volatiles are going to be released and help the mantle magma be formed in the mantle wedge. So key aspect here is the volatiles will rise up out of the subducting plate. They'll induce melting in the asthenosphere, and the main reason they can do this is actually to help break the silicate bonds and allow magma to be formed. So one of the things that I want to sort of tie in here is that you notice the decompression melting isn't really adding anything new. So basically, it's a fixed amount of magma that's there. In the case of the subduction zone, you're actually adding a lot of volatiles, and that's important because it allows there to be relatively high pressures that they can build up in these subduction zone volcanoes. And in those areas, you often see that there's additional hazards, not only because of the fact that there's a very thick continental and lithospheric crust that has to migrate through, where it can accumulate a lot of silica-rich minerals, but it also tends to be very volatile rich. So from a big picture perspective, we'll talk about this as we go on. These types of decompression melting volcanoes tend to be very volumetric, but almost have no volcanic hazards tied to them. In comparison, these volcanic settings where addition of volatiles at subduction zones create the magma, they tend to be very volatile rich, which steam can build up pressure. Carbon dioxide pressure gases can cause pressure to build up in a magma chamber and cause a lot of explosive material to be generated. And the second component is, here we pick up very little bit of the sort of upper continental crust or oceanic crust or lithosphere. Now the lithosphere again tends to be more silica rich as a starting composition than the mantle. So here we have very little bit of little addition of silica into the material that's entrained as the magma migrates, and as a result, these tend to be very, very quick flowing lavas that don't build up a lot of pressure or have very high explosive potential. But in these settings where you're picking up, material through the thick, again, 80 to 150 kilometer thick crust, you actually have great potential to build up sort of entrained silica melts or partial melts in the material. And as a result, these often tend to be very, very vertical, very explosive, and also have the potential to build up a lot of pressure in the volcano itself, which leads to a lot of the hazards we'll talk about as we go on. The third way that the lava can be formed, or magma can be formed, is actually the idea of the mantle plumes we talked about earlier in the semester, where you have a thermal instability at sort of the plate of the core mantle boundary that causes a thermal anomaly that melts, provides excess heat to melt the asthenosphere of the Earth. and actually allows that material to be transported up to the surface pretty readily. So the third mechanism, I suppose, is really just tied to hotspots. It's where you have extreme thermal anomalies. Examples again are Yellowstone, Hawaii, Ethiopian rift, where there's excess heat that drives melting from great depths in the Earth's surface. So as opposed to something that can be within the top 10 kilometers, top 30, 40 kilometers on maximum in the case of subduction, these are often sourced from greater than 1,000 kilometers in the Earth's surface. These still do, as we talked about earlier, remain fairly controversial and poorly understood. But again, most people believe they're thermal anomalies at the core mantle boundary. So putting this in perspective, again, any place where you have a plate interacting with each other, particularly in the divergent or convergent sense, you're going to see a volcano form. Those volcanoes will be tied to other potential hazards, with this plate tectonic cycle, such as earthquakes and tsunamis as well, obviously. But the key thing here is wherever you have a plate boundary that's a divergent, you're reducing the pressure. A reduction of pressure can cause magma to both melt and undergo upwelling, which will perpetuate more volcanic formation in these divergent plate boundaries. In convergent plate boundaries, most all of the volcanism will be formed by the addition of volatiles being carried down, which allows things that otherwise wouldn't melt and which wouldn't be able to make it through these really thick parts of the crust to build up enough pressure and enough magma body to become buoyant and rise up in these volcanoes. In both of those examples, I want to highlight here, you often see these long ridge systems in divergent boundaries, and we tend to call them volcanic island arc chains or arcs, of very vertical, steep volcanoes in the subduction zone setting. So these ridges tend to be very broad and flat, extend for dozens of kilometers away from the rift itself. These tend to be very high peaks, and this is what you can think about being in the Andes or the Western United States. To the point of this, in terms of the broader aspects of understanding the Earth and geology, is that what you actually find is something called we call it in geology a back arc basin. But that plate eventually goes down deep enough where the plate itself, or the subducting plate itself, starts to be volatilized, and that can often lead to another episode of melting, sort of paired between these composite chains, and then back deep in the basin, and those often lead to divergent boundaries that sort of break, sort of melt, cause a lot of volatilization, a lot of magnetism, and actually can cause continental rifting to break the plate apart along these boundaries. And this is sort of analogous to what you see over in the Basin Range today, where the plate itself started to be subducting very deeply. The plate started to melt itself. You saw the volatilization of the plate, which led to another episodes of magnetism, and actually leads to the emplacement of volcanics around Utah, Colorado, Arizona, New Mexico. And eventually, over time, can actually lead to another divergent plate boundary paired with this convergent plate boundary. But again, the same thing here. It's a volatilization-driven melting. The plume, of course, whether you want to think about Yellowstone, not shown here, again, is much deeper than what we're talking about. One of the other components I want to talk to you about here is that we talked here about divergent and convergent plate boundaries, but I didn't really talk about the transform plate boundaries. Is there any role of volcanism? And the reality is there is a very, very minor role of volcanism associated with transform boundaries. It can be thought of as basically being that decompression melting, where sometimes that transform can cause a little bit of pressure to release in an area, and you can see very small volcanic edifices being formed and being tied to activity in those areas. But really, they're inconsequential in terms of the amount of volcanism we see on the surface of the Earth. So to this point, I've talked a little bit basics of what the silica content means for flowing volcanoes versus sort of very slow flowing, ridge building volcanoes or shield, composite building volcanoes. What I'm going to do now is actually take you through the definitions of shield and composite volcanoes and what these mean. So basically, these are the nomenclature which we use to define what kind of volcano it is. So this is Mauna Kea in Hawaii. You can see the very broad, shallow slope which peaks up at the top of the volcano and goes down the other side here. And these are really, really wide, relatively flat slope volcanoes. And if you think about taking something like water and pouring it on an anthill, it's going to flow really rapidly off the side. It's not going to build up here slowly, right? By comparison, if I dumped a big jug of peanut butter on top of a hill, it might just sort of slowly build out with a really high peak in that area. So hopefully, just by looking at this, you can tell this is an area where the lava is actually going to be very rapidly flowing and spread out really, really efficiently. So the big aspects of the shield volcano, of course, are they're generally not going to be explosive. The low silica content means the lava can flow, and as a result, pressure doesn't build up in the magma chamber. So they're going to be, often in the low silica content, we typically call these basaltic rocks. So they're not explosive. They tend to be very big and very broad volcanoes. For perspective, remember, Hawaii, we see this as an island where this volcanism is above the water surface, but recognize there are multiple kilometers of water depth below Hawaii. So we think of Hawaii as a collection of islands. You actually need to think about it as a collection of big seamounts that are just huge topography below them that have put a lot of massive volcanism in those areas and just flow out over the top. Okay, so key things for shield volcanoes: shallow, gentle arch. They sort of look like a shield, very broad that you can defend yourself with. Is where they get their name from. And these are built up just episodically over millions and millions of lava flows to extend them out. Tend to have low silica content rocks, which means they're very low viscosity. And we call this type of rock a basalt. For perspective, the basalt is a type of rock that is formed at almost all of the divergent plate boundaries in the world. All the mid-ocean ridge, basically, it's called the mid-ocean ridge basalt. That's exactly what's released in those areas. So almost all the eruption is just flowing lava. Tephra ejections would be little minor explosions, but volumetrically not significant. And examples of this are Mauna Loa in Hawaii. Iceland's another example. But you can think of these shield volcanoes as being mid-ocean ridge type of settings. The other type of volcano, the other end member really, is at least the way we think about this, are the composite volcanoes. This is more analogous to dumping the big jar of peanut butter on top of an area. It's gonna basically, you might spread out a little bit, but it's largely gonna be vertical, very not very wide, very vertical, and sort of has more of the kind of classic volcano shape we're used to making in elementary arts classes, if you will. So key thing here is this is going to be much more viscous. As a result, there can be varying degrees of actually quite explosive activity with intermittent lava flow. So there can be lava flows, but often you see fairly explosive sort of high volatile amounts. The silica content tends to be higher. As a result, the silica content is higher than shield volcanoes. Tends to be relatively viscous, and actually, again, it's a cone builder rather than a big shield. And these sort of form a different type of rocks. Rather than, I should have said this earlier, this basalt tends to be very black. We call it mafic. It's iron and magnesium rich. It looks black, maybe a little bit of greens mixed in, but very dark colors. This tends to be andesite rich, or the rock type of andesite, which means it actually has quartz, which is sort of white or clear, and feldspars, which are often pink or tan. And as a result, these tend to be fairly light colored in terms of the rock itself. So composite volcanoes, cone shaped, very steep sides. They build up, sort of build up intermittently. They can be quite high. The reality there, though, is that the biggest competition for them building up higher and higher and higher is often themselves. They often start to build up to a certain point, and they'll have an explosion event because the pressure builds up too much. And as a result, they get these pyroclastic or sort of explosive dust deposits. Silica content is sort of intermediate. Andesite is just means that there's more quartz and other potassium and sodium-rich minerals in them, and they erupt with a combination of lava flows, but more commonly and more dangerously, the other end of that combination is the explosive activity. And there, Mount Fuji in Japan is an example of a current one. Mount Rainier is actually can be classified as a composite volcano in the western, in Washington State. Some people will intermittently call it a dome. So the third type is basically volcanic domes. Here's an example of one from Chile, and these domes are just sort of a top of a very high silica content rock. These tend to be most explosive. They have the really high silica content, almost a quartz-rich rock at 70%. And these typically form a rock called rhyolite. I want to stress here, I will not test you on the names of things like rhyolite or andesite, but this means that it's almost no mafic elements. It's almost entirely potassium and sodium, feldspars and quartzes. And the key things here is that these are just very localized, very vertical domes. Also kind of looks, I suppose, like what we think about volcanoes looking like from elementary school. But because of the high silica content, these domes can, even though they're relatively smaller compared to composite volcanoes or stratovolcanoes, these tend to be very explosive and put a lot of dust and debris into the Earth's atmosphere and also sometimes into the stratosphere. Generally speaking, these volcanoes are less volatile rich, so they're not as frequently as explosive, but there's a lot of variability there. And the last the fourth type of volcano is actually something called a cinder cone. You probably can get the sense here this isn't really the same scope or scale of any of the former types of volcanoes. And these are common, although they're relatively small volcanoes. They typically are just often what are called monogenetic cones. It's basically one little bit of magma makes its way up and explodes out into the surface. And they often tend to produce things like ash and pumice and just a little bit of debris. Most cases, these are singular events, monogenetic, often fairly small. And if you go out to Arizona, California, there's often scenarios where these become their own little independent mines. People are mining this for iron, ore, and things like that. So, again, relatively small. They can be associated with transform boundaries commonly, but the more common scenarios that are actually just found along the flanks of larger volcanoes or along faults, including transform faults, where there's just enough of a decrease in pressure or enough of a magma body that comes up in a volcanic setting that a little bit of lobe of that sort of undergoes melting and comes up in another location. So the key aspect of the cinder cones, small, little guys. They in general have no absolute chemistry, but tend to be low silica content and basalt-like. And most of their sort of ash and tephra ejection has little to do with their composition and more to do with the fact that they are sort of causing the crust in a certain area to become volatilized. They sort of have an eruptive way of breaking through the crust itself, and the areas near Flagstaff, Arizona, have many of these, which are quite scenic to see, for the record. So, to this point, we've talked about where volcanoes occur, right? Divergent and convergent plate boundaries. We talked a little bit about the nomenclature around what kind of volcanoes are out there and what they look like and how we define them. Really, the meat and potatoes of what I want to talk about in this class related to volcanism is understanding it from the back to the idea of sustainability perspective. How is it going to influence sustainability on Earth? How does it relate to the creation of geological hazards? Can it influence our potential to actually have sustainable societies on planet Earth? And the reality is, they can have pretty profound influences on society, on localized health if they cause there's eruption near population centers, and those can go from major changes, inducing major changes in climate. Obviously, there's examples of areas like Pinatubo or Mount Vesuvius where they can, it's very evident they can wipe out an entire, population center in an instant. And the point here is that they have great forces and great potential to do damage. But we're going to talk a little bit more about the mechanisms in which these hazards actually are generated. So the first one we'll talk about actually ties to lava flows themselves. These are, in many cases, not the most dangerous, but they're obviously something people tend to think about. And here's an example of a lava flow that flowed off this area, and you can see it sort of discharging out into the ocean. And this is actually still actively flowing out into the ocean and steaming up here, as you can see. And this is on Loihi in Hawaii. So the lava flows themselves, can either cool down very slowly by just cooling from the air, or they can actually cool very rapidly when they encounter something cold like a body of ocean water or something like that. So the two types of flows, I already alluded to this earlier, are the blocky or the flow, lava flows. And again, these tend to be more viscous, either primarily because of a higher silica content or just because they've had a chance to cool down more as they get closer to the surface. And these flow rates can often be relatively slow, a few meters of transport a day. This is an example, again, from Loihi, where this obviously this building is being, a house I presume, is being consumed by the slow flowing material as kind of advances, sort of pulsatingly, advance of slow flowing lava. And obviously, in this scenario, the risks, unfortunately, I'm not trying to make light of the situation, but if you're in this house, obviously you're toast. But in reality, from a hazards perspective, most of the lava hazards are actually pretty minimal. In essence, it'd be hard to believe you wouldn't be able to sort of identify seismic tremors, some a little bit of phreatic explosions, and then outrun this type of flow. So these tend to be very damaging, of course, where they're located, but by and large, people can avoid them, and there are pretty minimal risks for geologic hazards from these types of lava flows. The counter component of this, and these are both Hawaiian wars, I should say, is pohoihoi, and these tend to be the lower viscosity, both by a combination of lower silica concentration and higher temperatures. And the key thing here is that these types of lava flows can actually be relatively quick, and depending on the lava composition and temperature, can be exceedingly fast. So on areas like the Loihi and in Hawaii, these are a meter to a few meters per hour. The flows can be relevantly important, but in general, they don't do much damage to human life. They do damage to property, of course. But clearly, the pohoihoi lava flows are much faster and have a greater potential to actually cause damage because they move more quickly. And I'll give you an example of that here in a second. But one of the things I wanted to bring to your attention is that I kind of alluded to this example before, but this is the viscosity, which are measured in poise units, and effectively this gives you a relative amount of viscosity. Is water, olive oil, ketchup. I'd put peanut butter up here between basalt and andesite, really. But these basalts are the relatively fast moving. These can be pohoihoi. The cooler end of these basalts, or silica-rich end of these basalts, can be in the aa. And then actually, once you get above the andesite and rhyolite, these is where you get more of explosions, where they're not really going to move, and they have very high viscosity. So the key aspect of this, again, is that the silica oxygen molecules, they're the silicate tetrahedra, what sort of puts together the minerals and actually allows rocks, bigger minerals and rocks to form. They're the links that sort of put everything together. Less silica, higher temperature actually means that there are weaker bonds and the material can move more quickly. With more silica, strengthen those bonds, makes them more likely to be sort of explosive. So I'm going to go back here for a second. I mentioned this pohoihoi in Hawaii typically has about a meter per year. So I guess in essence, if I didn't make this point clearly, the risks of loss of life or human deaths by pohoihoi lava flows are relatively low. Unfortunately, that's not the case in every volcanic setting. So this is actually some work that I did during my PhD work. Seems like a long time ago now, but is actually related to a volcano in the Democratic Republic of Congo, right over here in Central Africa, and it's called Mount Nyiragongo. Okay, and this is actually right through here is the East African Rift that extends, from Djibouti all the way down through Africa. And this is a picture from the top of the volcano. We climbed up to the top of the volcano and actually, we climbed back down, repelled into this volcano, down and sampled lava and gases and all kinds of different things. But the reason we were there is not just because it's a cool place to go to or has a really scenic volcano and volcanic lava lake, which it, by the way, does, is because this area is one of the most continuously active volcanoes in Africa. It accounts for about 40% of all the eruptions in historical time in Africa. What makes this interesting is that the lava doesn't just move at a meter per day. It actually has very low silica concentration. In fact, it's what's called a silica undersaturated basalt. You can forget that word now. What it tells you is there's about 30 to 35% silica in the rock. As a result, if you pour this out, rather than being up here in the basaltic range, it's actually down here in the sort of the olive oil range. Um, Point being is from the top of this volcano, which is about 12,000 feet high, the lava can flow down the volcano or out of the side of the volcano if the crater wall breaches at about 60 kilometers per hour. So about a kilometer per hour, that's, 60, 70 kilometers per hour. So that's about, just short of a mile a minute for switching units there. But what you may know about is, if any of you have ever seen the movie Hotel Rwanda, there was historically some really horrible fighting and genocide in 1994 between the Hutu and Tutsi groups were fighting each other. And basically, there was a population of individuals that left Rwanda, were basically brought to Congo and put in a United Nations refugee camp. And that camp just happens to be on the east side of Mount Nyiragongo, just over here. And what happens is that on about a cycle about every 2 to 3, sometimes up to 5, but 2 to 3 is good average years, this volcano will build up this lava lake. Over time, the volcano will either overflow or breach. The lava will pour out at a relatively rapid rate, again, 60 kilometers per hour, a mile, kilometer a minute, about right. And there's a pretty high frequency that flow of lava will actually flow right through this refugee camp. So this refugee camp in 1994, if I have the numbers correct, about 50,000 people now. It's almost a million people. What happens is you have to relocate everybody if there's a high likelihood the lava is going to flow out of there. So I worked on this part of United Nations project, trying to mitigate volcanic hazards by basically understanding when the lava was going to flow, the likelihood is going to flow in these areas. I think it's a pretty incredible place. If you're into sort of the silverback gorillas, that's really they're all over here. Incredibly beautiful area, but it's quite interesting to see that these lava flows occur. People obviously have to move really quickly, and oftentimes that can lead to a lot of violence when people have to move away from those areas because of these situations, because they sort of get into situations where they move into somebody else's turf, and there's a lot of shortage of resources and stuff like that. But often within a few days of these events, you see populations moving right back in and setting up their houses and going back right on top of this just recently cooled lava. So for perspective, I should identify this before I go here, is that before I go on to the next slide, is that the distance between Mount Nyiragongo's crater right here and Lake Kivu, which Goma is the major city in this area, is now about 1 million or plus people, is about 12 kilometers. And as a result, there's somewhere between 10 to 15 minutes when this breaches that the lava can actually flow all the way down into the city of Goma. Just to give you some perspective, this is some work we did in 2003. The volcano was building up. The lava flow was, this is actually an after photo, I should say. This was taken in 2010, but the volcano basically filled up. There's a lava lake up near the top of the volcano. And then this is a picture, I think maybe a week after the eruption, where the lava drained out really rapidly. But what I'm trying to show you here is that, within 15 minutes, this lava flowed from the volcano up here down, into the city of Goma within 12 minutes. So this is the volcano. This is the perspective. This is the main street of the town of Goma, city of Goma. And these are houses. This here is all lava that just came down, poured right through the streets, and that's sort of where it stopped. Here's individuals climbing up on top of that. But for perspective, how uncontrollable this is. This is the Goma International Airport. Here's the jet fuel containers. Here's the lava that flowed right down into the airport. And here's actually the airport field. That's a Boeing 747 for perspective, where the lava flowed right down into the airport and covered the area. Obviously, that's flows right in the streets. Here's an individual who's just poured down, like he's just walking away from the area. But this is literally just where it stopped and stopped flowing. So here's just some pictures if anyone has any interest in this of us. That's this is me down in the volcano. That's one of the members of our team going down to sample. And this is the Dario Tedesco. He's the chief UN hazard mitigation expert who we worked with down in their sampling. And these are our guards. Make sure no one minded us when we were up there. And then this area is really between the volcano and the refugee camp is really quite a conflicted zone. It's one of the main breeding areas of the largest wild silverback gorilla populations. And there's a lot of folks who are trying to develop this as an economic resource for the area. So for clarity, the Yellowstone National Park was the first national park in the world, and this national park that encompasses Nyiragongo volcano, the Nyiragongo, the Virunga National Park, which encompasses Mount Nyiragongo, was the second national park ever made in the world. And what happens is Congo's consistently had development challenges and sort of lurched forward and backwards. And they've been trying to develop the park as a resource to bring in tourism and bring in an economy. And some of the rebel groups, if you will, in the area have been actually very actively trying to kill the silverback gorillas because that's the main attraction. So they go out and sort of poach them to make it less appealing for people to come there. And this is actually, we just went to here. This is an area where there's a silverback gorilla, orphanage that's actually there. So this is, wasn't part of the team that found this guy, but he was found during our trip up here, and we went to the orphanage before we saw him. Just for interest, I show this picture not because it's a beautiful picture of life in Goma, but actually because the state-of-the-art way that people locally would predict when the volcano is going to erupt, back 20 years ago, was by burying bananas in the ground. That's something they do routinely. There's ample bananas and chai and tea and coffee in the area. But what they do is the local beer was actually made by burying bananas in the ground, allowing the bananas to ferment, and then making, for alcohol, and making beer, which actually was pretty tasty, by the way. So we went from, turn of the last century, people using bananas to predict when volcanoes erupt, to now doing, I won't bore you with this, but making all kinds of complicated gas measurements and seismic data and stuff like that to try to estimate when it was really going to happen. So rather than getting on to the next aspect of volcanic hazards, we only have 2 minutes left. I'm going to stop there, and we'll pick up on Wednesday. Just a reminder, the worksheet for this week is online already. It's already been posted. It's, again, due by Friday. We're back on our normal schedule. And we'll pick up on Wednesday with our next lecture on volcanic hazards. Hope everybody has a great week.